where the potential cancer. Second, actually try to talk about the lesion, where the malignancy is. And the third category of software, that the CAD-Q category, that try to quantify if there is a tumor, if there is a lesion, what is the shape or what the size of the lesion. Maybe you are trying to find out the texture of the lesion or maybe the shape of the tumor. So that can be identified by quantification. So there are three different subcategory of computer-aided diagnostic system. So a person who is working on computer-aided detection may not work for diagnosis, or those who are working for the detection and diagnosis may not work for the quantification. So these are the three typical categories of software where people generally try to work, and which comes all under one particular category, which is called clinical decision support. So that is the overall idea. Now, talking about this different medical modality, if you look into, say, CT image or MR image or UV image, ultrasound image, or maybe any other, say, for example, endoscopy, or maybe retinography, maybe ophthalmo images you are dealing with. So we'll see almost 70%, 70+% of the whole imaging, different modality, imaging modality are, say, so-called, you can say, these are basically very perturbated, dark, noisy images. And we need to deal with such kind of noisy, perturbated images. And once we try to deal with this kind of knowledge, such kind of images, why we need to store this whole data set, whatever the data set we are having, into a CAD system. So basically the radiological images we are talking about 70+% radiological images. Remaining few other cases, like, as I said, ophthalmo, maybe derma, maybe sometime you are dealing with, say, endoscopy, maybe those are not radiological images, but still CAD can be deployed. But mainly CAD system can be deployed into radiological images. That is the main thing. Now, talking about this CAD system, what this CAD system actually is, it's nothing but a typical pattern recognition problem. Now, whenever we are talking about pattern recognition problem, it's nothing but something dealing with a stored pattern, and we are trying to identify if there is a new pattern, is there any similarity or dissimilarity in between these two. Say, talking about an X-ray image, if there is an X-ray and there is a hairline crack, we try to identify if this is suspicious one or not. So if I try to find out this, we need thousands and thousands of images which need to be put into a CAD system, maybe CAD server, maybe in the form of, say, diacom image or maybe QTV image format or any other image format. And from those stored data set, we are trying to identify if there is new coming any pattern, if this is matching with the stored pattern or not. So nothing but this CAD system is, in a one line, you can say it's a very, very difficult high level pattern recognition problem. Now, talking about this pattern, once we talk about this pattern is nothing but a repeated kind of sequence, something which is happening in a repeated way, in a regular way, something which is happening in a very systematic way, we used to call that is a pattern. Now, talking about the pattern, the very first pattern comes into our mind is the Fibonacci series. Now, talking about the Fibonacci series, something like, say, for example, 0, 1, 1, 2, 3, 8, and gradually if you proceed, you will see in Fibonacci series, there are some certain inherent underlying pattern. Now, what type of pattern? The pattern is, say, for example, you are taking 2, 3, 5, 8, 13, these numbers, and this number has a width and as a height. So it's a square number, 2 as a square, 3 as a square, 5 as a square, or 8 as a square. You will see it's nothing but giving you a complete shape of a spiral. So basically, Fibonacci series actually followed a spiral shaped structure. Now here, this underlying pattern, we are talking about this Fibonacci series. One starts from, say, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and gradually you will see it will give you a complete spiral shape. Now, if you follow this pattern, you will get another pattern, which is called a golden ratio. Say, for example, you take any two number, say AB, say, for example, 2, 3, or 3, 5, or 5, 8, or say, for example, 144 to 33. Now you divide B by A, and you will get a number which is very, very close to 1.618. And initially the number is very semi-fluctuating number, 1.5, 1.66, 1.6, 1.62. But as you move, as you proceed, because this is an infinite length series, Now, once it is an infinite series, if you gradually move and divide all B by the subsequent A, you will see you will get a number 1.618. Is almost close to 1.618. Now, what happened? If you follow this golden ratio, you will see this ratio 1 is to 1.618. This ratio, this spiral shaped structure, is followed in nature many places. Say, for example, the rose. You are trying to identify the pattern of a rose. So rose actually follows a pattern which is nothing but 1 is to 1.618, which is nothing but a golden ratio, which actually follows as a spiral shape. Now, talking about, say, for example, sunflower, or maybe any, say, galaxy, or maybe any kind of, say, cyclone, you're talking about an egg, or maybe a pangolin, maybe cauliflower, maybe the continent. Everywhere you will see such kind of Fibonacci series exist. Even for the Mona Lisa, if you look into Mona Lisa, even your own face, you might find something like 1 is to 1.618 ratio. So even if you look into a biometric, say, print, there is some arc, there is some, say, bifurcation in the ridge are there in your fingerprint, you will also get such type of Fibonacci series there. Now the question is, do you think such kind of actual, this kind of series exist, or these are simply we are trying to impose? The answer is very simple. There is no as such kind of pattern exist. We try to impose such kind of pattern. Actually, in reality, there is no as such kind of pattern exist. Now, this famous golden ratio, what is the use of this? The use is we try to conceptualize some information. Whenever there is a pattern, we try to store it, we try to memorize it, we try to recollect, we try to recall something. We always try to impose some pattern so that it will be helpful for us to conceptualize the information. So that's why the underlying line is there is no as such pattern exist. It's all about approximation. We are trying to impose some pattern so that it will be easier for anyone to conceptualize the information. That is the whole idea. Now, if you look into this particular diagram, I mean, some of you might tell that this is a diagram of a circle. Some of you might say, no, this is not a circle. It might be a square. But I think none of you will actually imagine that this is not a square, not a cycle. The circle, why not this is circle? Because it's a kind of discrete pattern. There is some breaking in the whole circular, this line. So the idea is whenever we are trying to map something, we have some stored pattern in our brain. We have the stored pattern that square looks like this or the circle looks like this, but it never comes to our mind that this is not actually a circle, this is not actually a square. Rather, we always try to map with some stored. This is an approximation. An incomplete picture can imagine to complete the impose of the pattern so that you can actually try to recall or recollect or memorize that how good your stored pattern is with this existing diagram. So that is the idea. So even though there is no such kind of pattern, but our brain always try to impose it's a circle or it's a square. Now talking about human brain is very complicated thing. If you try to store the information less than 1 second, it's called a sensory memory. So we have different sensory organs where we should not store the information more than 1 second. Now, if you have a very short-term memory also, that is called the working memory. If the memory works for 1 minute or lesser than the 1 minute, so that is called the short-term memory. And there is another memory which is called the lifelong memory, which is a lifetime memory. And that can be conscious, that can be unconscious. One is called the explicit memory, one is called the implicit memory. So if you have a skill, something task you are trying to do, that is called the procedural memory, that comes under the implicit memory. Now, if you are trying to map the pattern with some event, some experiences, say during COVID period, I did this. So it's a kind of episodic memory, or which comes under declarative memory, which is an implicit memory. The interesting point is this conscious and unconscious memory, which all comes under this lifelong memory as a human memory part. I mean, you can say the 3 category. The human memory can't store more than 7 ± 2 number of chunks at a time. So at a time, if I ask you to memorize 7 numbers, 7 mobile numbers, you make, if your memory is very good, maybe 5 or maybe 9, you can at a time, you can say. but it's very difficult if it's go beyond 9. So human memory have a limited capacity. It's proven that Professor Miller in 1956, they come up with an interesting work. They said that human memory having a very limited capacity, 7 plus minus 2 number of chunks. And there are two methods to memorize something. One is called recall the sequence in order. One is called recall the sequence in any order. So if there is say tables, you are trying to talk about table 2 or say table 3. It's a kind of, you are trying to recall a sequence in order. But once there is a phone number, mobile number, it's not in sequence. So you need to come up with some pattern. You will try to identify, okay, within that particular phone number might be 47 is there. So it's an independent, so 47 is there. Or maybe 2 consecutive 3 are there. Maybe 3 consecutive 5 are there. So you are trying to find out some pattern, even if it is not in sequence, to recall a particular thing. You are trying to come up with some hidden pattern, identifying hidden pattern. That is the objective. Now, if I say what is written over here, HECAT. Now, simply look at the diagram again. Look at the slide rather, and write down in your text box what is the sequence. So again, HECATRANUPTHETREET. Now write it. Anyone? Just try one time by yourself. If you say I can show one more time. Okay, again. So conscious memory. So one time, HECATRANUPTHETREET. Now, if you try to write it in the chat box, I can get an idea that, rather I can tell you that what exactly I'm trying to mean. Can anyone? Okay, somebody have written HECT. Okay, if you not copied, it's very difficult. If you copied it, it's easy. See, the idea is if you take the T and put it into at the very beginning. So if you take the T and put it at the very beginning, you will see the cat run up the tree. So what the thing is, it's a non-sequence, but we are trying to impose some pattern. And once we try to put into some sequence, it will be easier for all of us to recall. So the idea is this. So that's why how good your memory is to memorize. Even a human memory, how good your memory is, you can actually mark with 4 different measures. The first measure is called read integration. What is read integration? I will give you some partial clue. Based on the partial clue, you have to come up with the whole thing. That is called read integrate. So you are trying to read integrate based on some partial clue. Second thing is called the relearning. That means you need to reach a particular competency level and you are started learning, relearning, and you are trying to reach to the competency level. If you reach, then you go for unlearning. One is called the recall. How good your memory is to recall. You need not to give any kind of partial clue. Without any clue, how good your memory is to recall. So one is read integrate. It's a kind of phone a friend. I will give you a support. I will give you a partial clue. Based on that, you are trying to read integrate. You are trying to reach a particular level, competency level. How good your memory is to relearn. How good your memory is to recall without any partial clue. And the last one is called recognition. There is no clue. There is no partial clue. There is no competency level yet. You have to reach or reproduce something. I will show you some content you have to reproduce. So that is called the recognition. Your subject is trying to identify correctly the reproduced one. So that is called the recognition. So once we talk about recognition, and cognition. The cognition is a kind of process which is directly linked with our brain. We try to match with some information we encounter with the stored data in our memory. So if our memory has something, we are trying to map with that. That is a cognitive behavior. The process of knowing an entity is called cognition. And recognition means it's a kind of process of knowing something entity again. You are trying to reproduce. So that's why the terminology is called the recognition. So that's why I think now the idea of pattern, the pseudo pattern, the imposed pattern, how the pattern actually looks like, and why we need to recognize these things. So that is clear. So that's why once we talk about these CAD system, computer diagnostic systems, it's all about identifying the typical pattern which is stored into our database and identifying those patterns for a newcomer, just to map and come up with a decision-making process that how close this is with the stored pattern. So that's why it's called it is typical high-level pattern recognition problem. Now, once we talk about the pattern recognition, you are trying to go for, say, for example, you are trying to categorize A, categorize B, so disease, non-disease, whatever it is, maybe by means of some known category or maybe unknown category, maybe supervised form or unsupervised form. What is a so-called classification and clustering paradigm, where we actually try to map the pattern with the stored pattern. That is what we actually do for all these CAD system design. Typically, this all computer system try to come up with a decision-making process, identifying the pattern, and talks about the decision-making final. I mean, it helps the doctor to come up with a rational decision. You are having disease or non-disease. That is the idea. Now, this was the first part. So what is actually CAD system? What is the function of CAD system? And what is the pattern and what the recognition process is, and how pattern recognition is interlinked with the CAD system. So now we will try to move to the image processing part, which is one of the, you can say, the part of a core part of CAD system, any CAD system. The first thing is the image which we used to process, we used to get rather. Majority of the image are very perturbated image, noisy image, dark image, and quality compromised image. So we need to go for pre-processing. So we need to reduce the noise level. Sometimes we need to go for leveling. Sometimes we will need to go for filtering. So that is the so-called pre-processing steps. Then we try to come up with a segmentation strategy. There are n number of segmentation algorithm by which we try to identify which is your region of interest, which is your non-region of interest. We try to separate out that this is my region of interest, ROI, and then we try to go for finding the structure of the ROI, the compactness, the size, the location, the form, maybe by analyzing different features, etc. And ultimately, once you get those structure of the ROI, then we put it into some classifier, then shallow machine learning period. What I'm talking about before 2012, that time we try to come up with some different the classifier result. The outcome can be a, say, disease or non-disease. Based on that, we try to evaluate. So the idea was something like CAD system comprises 4 different things. One is called the recognition and modeling. Before that, there is definitely segmentation and quantification. Then comes the decision support system. Then comes the visualization part. So if you have an image database, then you read the image, you go for pre-processing, extract the region. Then after ROI extraction, go for feature extraction, put it into classifier, whatever the so-called ABCD classifier, they give you some predicted result and they give you some diagnostic result. That is the whole idea. And I'm talking about these whole model of CAD system, maybe 13, 14 years back during the period of shallow machine learning. But once deep learning introduced, that period, once AlexNet introduced rather, from then onwards, there is a paradigm shift of CAD system design. But I am initially trying to focus on this most traditional one, the shallow machine learning period. Then gradually I try to move to the deep framework. Now talking about this image segmentation, we try to divide the image based on the gray level, color, texture, brightness, contrast level. But for image segmentation, there are different challenges. One challenge is called partial volume effect. Say, for example, I'm talking about a particular disease which is called atherosclerosis. What is the disease is, once you are getting aged, say maybe around 60 years, if inside the artery wall, the blood is flowing, but inside the artery wall, maybe because of your food culture, because of your different reasons are there is some deposition of calcium. Now, once there is a calcium is getting deposited inside your artery wall, and calcium is depositing and increasing in volume. Now, what will happen? The blood will suddenly get stuck and it will not move from your coronary to your carotid to your brain. and you will have cerebral attack. So that's why the idea is you have to put a probe. The probe will move inside the artery wall, artery rather, and the probe will rotate and it will emit sound wave. Once a sound wave is refracting from the inner wall, if there is a calcium, the refractive index, if there is a non-calcium region, the refractive index will be different. So based on that, you try to find out how much calcium is amalgamated inside your artery wall. Now there is a therapy which is called balloon therapy. If you put a balloon and the balloon getting blast, then immediately all the calcium it will actually take out from there, and you will see the passage is getting not narrower, it is getting broader, and more blood will circulate, and there is a chances of stroke will getting lesser. Now the idea is once you put the probe having some shadow. Probe is nothing like a stick. Now the probe having some shadow. So within that shadow region, if there is some calcium lies, so within that shadow region, if there is some calcium lies, even if you try to segment the wall, you will see the result will not correct. This is called shadowing effect. I can give you a different way, an example. Like say, for example, from a drone, you are trying to capture the image of some vehicle. There are 4 buses, and beside the bus, there are 2 cycles. Now, bicycle, the shadow of the buses covers the bicycle. So until you remove the shadow, you'll not be able to find out how many number total vehicles are there. So that is what the idea is called the shadowing effect. So first thing is this is one problem. Second thing is the calcium is not deposited in a single place. It deposited all around the path of the wall. So there are small calcium. If it is amalgamated in one place, it's very easy to segment. But if it is amalgamated in different places, small chunk, it's very difficult. Intensity, inhomogeneity. The homogeneity is not there. Even you see, majority of the cases, there are a lot of artifacts, false noise. So that can be also there. And the closeness of the gray value, because all these radiological images, they are almost very blackish kind of image, and the gray level are very closer. So once there is a closer gray value, it's very difficult to segment those images. So these are few of the typical problem of medical image segmentation. This partial volume effect, shadowing effect, intensity, inhomogeneity, presence of artifacts, closeness of gray value, etc. Now, once you go for any segmentation strategy, even if you talk any segmentation strategy, you will see there are 3 different categories. First category is histogram level based. So if you have threshold value, 2 threshold values, say for example, 55 and 200. Now from 0 to 55, you are thresholding based on 55, first segment, 55 to 200, second segment, 200 onwards, third segment. So T1, T2 is 52 and 200. Based on that, you can segment your image by analyzing the histogram. You are actually partitioning your image into 3 different gray values. So 0 to 55 will be represented by 45, 55 to 200 represented by 120, 200 to 255 will be represented by 210. Say for example. So 3 different gray value. Now the problem is how to finalize this T1 and T2 value. This 55 and 200 will be your T1 and T2 threshold value. This threshold value selection will be different for different modality, different patient. Even the alignment of the patient is getting changed, the T1 and T2 will be changed. So that's why what I'm saying is this T1 and T2 finding, this threshold value identification, is itself an optimization problem. Now, talking about these 2 particular image, the limitation is of all these gray value, histogram based segmentation strategy. If you look into these 2 images, it seems to you these 2 images are different, right? But if you carefully look into the histogram, RGB of these 2 images, you will see their histogram are exactly same. Professor Pass in 1997, they reported these 2 images where they shown these 2 images color histogram, RGB histogram are exactly same. So based on this histogram, if you are trying to segment your image, it might not give you a proper result. So there are 2 limitations. One limitation is the artifacts which is present there. Based on that, if you're trying to threshold your image, the selection of T1, T2 value, the selection of threshold value is a kind of optimization problem, and it will be different outcome, different segmentation result for different cases, first thing. And second thing is the color histogram. The problem is a kind of typical problem, which is actually I already discussed. It's 97 paper. Now, second one strategy is called the age-based segmentation. Any segmentation which is basically based on the age. There are n number of segmentations are there. Now, if you look into this age-based strategy, you will see in the age, it might happen the noise is present in the age. So whenever you are going to detect the age, the contour, you might think that, okay, I have correctly identified the age, but actually is nothing but noise. So that is called false age detection. So whenever you are trying to detect some age, and if it is based on the false age, which is generated by the noise itself, which is a very common in medical image, now ultimately your segmentation result will be not good. So that's why the main limitation of age-based strategy is false age identification. Now, if you go for pre-processing, it might happen you are continuously losing the age information. So you are trying to blur your image and continuously will see you are losing the age information. So that's why designing of a filter which will actually not work whenever there is an age. But if there is no age, it will work. So that is called age preserving smoothing filter. So age preserving smoothing filter itself a research area where people try to come up with filtered strategy. The filter will stop working once there will be an age. Otherwise, you will continuously lose the age information. Because of this pre-processing, you are trying to make it blur. Say, for example, you are using median filter. There is, though city images don't have such kind of noise, salt and pepper noise, but say, for example, there are salt and pepper noise. There is basically speckle kind of noise. But once there is a salt and pepper noise, you are deploying some median filter. It will actually remove the age information, blur the age information. So we need to come up with some filter. It's not like median filter. It's not like Gaussian filter. We need to come up with some filtering strategy which will actually preserve the age information. Remaining all area, it will work fine, but not in age. So if there is a change of dy dx, if there is a change of gradient, the filter will stop working. And remaining any other places where there is no change of dy dx, the filter will work. So that is the whole idea. And the third one, the third category is called the region-based segmentation. So region-based segmentation is in the image itself, you try to find out some points. Those points, based on those points, you are trying to grow the region. So one is called region growing. The similar kind of gray value will be merged, or you try to come up with a large size and try to split it. That is called the region splitting. So one strategy is called the splitting strategy. One is called is the merging strategy. But the problem is how many numbers of segmentation you require. There is no predefined kind of this number of 50 number of segmentation we require. So the algorithm sometimes gives you over segmentation result, sometimes give you under segmentation result. So again, the optimal selection criteria for the number of segmentation, how many numbers of segmentation will be there, that need to be identified. That is one problem. And second problem is this under segmentation and over segmentation. So if you have some brain disease and you are going for some under segmentation, the medicine might not work. If you go for, say, over segmentation, might be the patient can have a stroke. So that's why it's very, very vulnerable. So if you look into any segmentation strategy, image segmentation strategy, actually whatever the algorithm is, you will see either it comes under, say, gray histogram based category, or maybe region based category, or maybe the another one is the third one is a age based category. But people try to combine this. They come up with hybrid approach. Sometimes they combine the age based with the histogram based, or the histogram based with the, say, region based. So in this way, they combine and they try to come up with some hybrid technique. Hybrid technique, again, it's a very good technique. Sometimes it gives you very effective result, but ultimately the complexity getting much, much higher. It is not recommended that your image segmentation strategy will take so long time that the patient will have no benefit from it. So it should be very fast. So that's why hybrid techniques not always good. This is one example of a contour-based model, which is an years-old algorithm again, 1987. So there is a elliptical shape curve, the parametric curve. You are trying to fit in the curve. If the image is very small, it try to find out, it try to fit the curve in the lesion. How it try to find out? If the energy level is minimum, it will simply struct over there. So you are trying to fit a curve, parametric curve, and you are trying to catch where the lesion actually exists. So that is an energy minimization problem. You can see it's a kind of age-based strategy also. Again, it's a region growing strategy. So you are trying to split and merge. So it's a kind of region-based strategy also. It's a global region segmentation. Again, it's a contour-based strategy. Active contour model works very, very nice for many of the medical imaging cases, ones who are dealing with medical image. But there are a lot of variations also. Say, for example, one variant of SCM is called snake model, which is again a very interesting segmentation strategy. But if you look into any other segmentation strategy, say for example, based on k-means, C-fuzzy means, or say watershed, or any ABCD, any segmentation strategy, you will see it always comes under any of these three categories: age-based, either, or region-based, or it's an histogram-based. But all these different segmentation strategy have their different types of limitation. So whenever you are hybridizing any two strategy to come up with a segmentation outcome, you have to remember that all the limitations, again, it is getting doubled. So you are simply increasing the complexity as well as the limitation might get also increase. So that's why very carefully we need to select which particular segmentation strategy we will adopt for medical image processing. So after pre-processing, the second step was finding out the region of interest by segmentation. So that is how it works. So once you have segmentation result, then parallelly you should have the doctor's hand trace result. So if there is a tumor, the tumor is drawn by the doctor, hand drawn, and parallelly there should be a software generated one, your CAD system generated one. This is my age of the lesion. Now, if say for example, the ground truth, the doctor's hand trace is red and the software generated CAD system generated segmented outcome is the signal, that is a blue. Now, if they are very close to each other, the variability is very less. We used to call measure by figure of merit, FOM. So how good your segmentation is. If the variability is very less, that means your outcome, the segmentation outcome is close to the doctor. If the variation is very high, that means you are far away from doctors. So that's why figure of merit needs to be studied. Sometimes we used to call precision of merit also. And the F measures, different F measure value actually tells you how good your segmentation is. So whenever you are going for segmentation strategy, deploying segmentation strategy, the second step is you have to benchmark, with the ground truth. You have to compare with the ground truth, the doctor's hand trace, that how good my segmentation is. One is called inter-observer, within the observer, or intra-observer variability between observer, means between two doctors. So one doctor can benchmark 2 times, or maybe 2 different doctors can benchmark 2 different times. So within this, we can come up with a, say, rational averaging, and we can compare our outcome. That is the idea. Sometimes it might happen that in medical imaging, it's not always automated. Semi-automated also works fine. So say, for example, this is a case where the optical cup and the disc of the diabetic patient not clearly identified. So it's not, say, for example, we are trying to detect the optical cup and disc. If it is above 0.58, the ratio, then it's a clear case of diabetic retinopathy. Now, what happened if because of the, say, contrast level, because of the brightness, if you failed, your automated system failed to detect correctly the ophthalmic cup and the disc, sometimes you need to put some marker or the pointer, which will drag by the doctor and they can freeze it. So it's a kind of post-processing. So 99 cases, your software correctly detects, segment the eye, the ophthalmocarp and the disc, but maybe 1% case is not correctly identified. That time human intervention is required, and you give a platform to the doctor, draggable functions, which will help the evaluator to evaluate and come up with a proper result so that the classification accuracy will increase. So that is the idea, which is called the semi-automated segmentation. So I think I need 1 minute break, then I will start. In between, if anybody having any query, please write in the chat box.
Anybody have any query? Then she can write in the chat box so that I can answer afterwards. It's very interesting area, like many people are working on the image processing, specifically in medical imaging. These techniques are very much important for pre-processing to identify the region of interest or region of area, region of interest if you want to calculate. Then these methods are very important. You are not audible, sir.
Okay.
Now audible. Yes.
Now it is audible, right? Fine.
Yes, audible.
Okay. Now, once you get this segmented outcome, then the second thing we need, we have to extract the features from those segmented region. So very first segmentation after deploying the segmentation strategy, we need to come up with the color features. So one feature is a prominent feature. Say, for example, you are dealing with diabetic retinopathy. So diabetic retinopathy can be different type. It can be soft exudate, it can be macrocalcification, it can be hard exudate, it can be hemorrhage, it can be dorsal, etc. So there are shape is different, size is different, roughness is different, the edge sharpness is different. All these things will be different. Color will be different. So looking into the color, you visually can prominently discriminate that these patient having hard exudate or soft exudate or macrocalcification. So color is a prominent feature. And second feature is a texture feature. Texture feature is, say, for example, you have a microscopic images. It's a rat brain, and there is a cancer growth. So fibrosis is there, and different fibrosis level 1, level 2, level 3. Now you are trying to mark into small pieces, and now are intermingling those. So all those patches are clearly, prominently, you can identify this particular feature is for fibrosis level 1. This is for fibrosis level 2. These are for fibrosis level 3. So you are trying to categorize by feature. So these are the corresponding book. You can actually go through this book that it's talk about only about the texture feature. Now the third one, before going to the third one, color and the texture. If you look into the, say, for example, if you are dealing with, say, breast cancer. Now the breast density, if there is a fat or fat granular or dense granular, it can be clearly, prominently, you can classify based on the color, based on the texture. If it is gradually getting whitish, that means it's the granular part is getting more denser. So from fat to fat granular to fat dense, you will see there is a prominent change of texture as well as the color. So color and texture is a prominent kind of feature. From medical, any modality you will see is clearly visible. And the third one is a shape-based feature. What is a shape-based? Say, for example, you are dealing with teeth. And in the teeth, there is a inflammation. And the inflammation is a kind of periodontal ligament is getting inflamed. Now, how can you actually train your system with this particular shape? What is the shape of that particular, say, inflammation? Now, you are trying to fit an ellipse. If you put the ellipse, you will see how much from the geometric shape and the inflamed part, that's the non-geometric shape, how much it is getting deformed. So you are training your system that the original, the actual shape of the elliptical shape is something like this, and the deformed shape is like this. So this much you need to train to your machine. So that is called the shape feature, by which actually in CAD Q, the quantitative one, we try to quantify what is the size or what is the shape of a particular lesion or tumor or wound or maybe inflammation. So that's why there are three typical features. One feature is called the color feature, one feature is called the texture feature, one feature is called the shape-based feature. So if you are dealing with any kind of hydraulic feature, GLCM feature, say Gaussian feature, wavelet feature, ultimately the bottom line is you are trying to identify either shape-based one or maybe the color one or maybe the texture one. But in between something, maybe something geometric also there, but geometric is actually related with the shape feature. So you have a lot of different features. Once you have all those features, you have a large number of features and the data size is small, because X-ray might be you are having 500 X-ray and you are coming up with 100 features. So the matrix will be 100 to 500. Now, what is the problem? The problem is there is a high chance once you're extracting more and more number of features, there will be duplicate feature, poor predictor. So you need to rank. You need to come up with some ranking strategy. You need to find out searching strategy by which you can find out these are the good number of features. So there are a lot of feature selection algorithm. You try to go for the reduction algorithm also. You can deploy say PCA or LDA, so-called the discriminant algorithms, means you are trying to reduce the dimension of the features. From 100 features, you come up with say 50 features or 30 features, which is a good number of features, and you deploy those features for the machine learning purpose. And ultimately, we used to do in two ways. One is called the filter method. One is called the wrapping method. So filtering technique is if your response and the feature, one is continuous, you go for Pearson. If your response and the feature is say for categorical and continuous, or categorical, or maybe categorical continuous, you go for ANOVA or maybe chi-square or maybe LDA. So you deploy on this. But the idea of filtering is you have a large set of data, you have a large set of feature, you exclude features which are not related, which are poor predictor, which are redundant, where the similarity is very less, or maybe if the similarity is too high, they are close to each other, that means you need not to incorporate both features, you can exclude one feature. So that is the idea, how can you filter? And once you go for wrapping, you come up with small number of feature, then you include more and more number of feature, so that the feature pool will get larger, which is called the wrapping technique. There is another third category, which is called hybrid strategy, where the filtering method and as well as the wrapping method combine to form a hybrid strategy. So that is how the selection approach actually works. So once you have all those features, selected features, reduced feature, then you put it into some classifier. And whenever you will use some classifier, maybe support vector machine or random forest, or maybe the decision tree, whatever you are using, you should have a particular, say, logic behind it, what the philosophy behind using that particular classifier, why your random forest is giving better result, or maybe XGBoost is giving better result. So you need to justify why this particular classifier is giving better result than rather than this one. Sometimes maybe if you are giving decision tree is giving better result. So why decision tree is giving better result than random forest? This need to be justified properly. Then ultimately you get a number, and those numbers will tell, okay, 90% accurately your CAD system can detect cancer growth. That was all about the shallow machine learning period. So pre-processing, quality enhancement of the image, then go for segmentation. After segmenting that, finding out the region of interest, go for feature extraction strategy. Then once you deploy it, go for selection, go for reduction, then put it into classifier, get some numbers, and those numbers will tell you this much is the accuracy of the whole model, maybe the precision, recall, AUC, ROC, etc., and you are happy. So this was all about the traditional machine learning period where I'm talking about before 2012. So that time, once deep learning first time introduced, the manual extraction process, because all those processes are actually biased somehow, because you are trying to come up with the decision making process, which particular segmentation I will use, which particular say classifier use, which particular say feature extractor I will use. So it's all human intervented. So that's why we need to come up with a more generic and rational framework for CAD system, where the local patterns combine into a more larger pattern, and more larger pattern combined to get a more and more larger pattern. So that was the main motivation to come up with a more faster and rational and generic framework where the human intervention will be very less, and ultimately CAD system will give you a better result. So that was the motivation from switching from the traditional shallow machine learning to the, you can say, so-called deep framework. So this is how actually it evolved. So input image, go for feature extract selection, classifier, result. That was the traditional machine learning. Now, once we talk about the deep framework, it's simply input image, neural network, and finding the result. So in between, how the image is getting acquired, what is the quality of the image, what is the, say, measures you need to take for the pre-processing, what are the measures you need to take for the segmentation, what are the measures you need for the selection of these features, that need not to be decided. It's a simple kind of framework, but there will be input and output, and you will get a result. So that CAD system actually deals with a lot of data, high accuracy, rapid processing time. Now I'm moving into deep learning. Deep learning is nothing but a representation of a better kernel. So once you are trying to solve a particular problem in a shallow machine learning framework, your kernel is not be able to solve that properly. You are trying to come up with a better representation of the data in such a way that the kernel can fit in and give you a proper result. So it's a kind of optimization of hyperplane fitting into a problem solving purpose. So that is a better representation of data, is called the deep learning. Now, here is an example, Professor Goodfellow. He tried to actually give these, there are two different geometric shape. One is circle, one is triangle. Now, if I try to ask you that if you draw, can you draw a straight line to separate these two data? It seems to you that this is not possible. If I draw a straight line, how can it separate? But think in a different way. It was in XY coordinate, Cartesian. Now, if you change into polar, r theta, it will look like something like this. Now, once it is something like this in polar, now drawing a straight line will be easier. Now, from polar, if you back to Cartesian, it will be again a circle. So that means it's nothing but a better representation of the data so that the hyperplane can be fit in an optimized way. So that is the learning, the automatic searching process of the representation we can do in a better way. So that is called the deep learning. That is the essence. Now, once we talk about deep learning, it's talk all about the large data set. Now, before going to the large data set, let me give an example. Pi computation, 3.1415926 ... Now, how many numbers of decimal points? Some Swedish scientists in very recent time in 2021, they've able to find out 62.8 trillion digits. 62.8 trillion digits. Just to prove the superpower of machine, supercomputer, and just to prove what is so-called big data, which you all need for actually machine learning. Now, think in a rational way. How many numbers of decimal point we actually required? To find out the circumference of Earth, we required only 10 decimal points. To find out the circumference of Milky Way galaxy, which is our, you can say, nearest galaxy, how much decimal points we need to, for this computation? 32 decimal points. How much decimal points we actually required to find out the observable universe? Planck length, that too, 65 decimal points. How many actually you computed? 62.8 trillions. And I'm talking about 65 decimal. So what about these 62.579 trillion digits? Are they scientifically significant? Or we are simply producing those data just as a garbage, or maybe the digital pollution, better to say pollution, not as a garbage, where simply we are creating the data just to prove the superpower of our supercomputer and just to prove what big data actually mean. But all those data are not scientifically meaningful. So that's why data is important. But what type of data is a big question. Now, any machine learning algorithm, the intrinsic nature is data hungriness. As much as data you will feed, you will get much and much better result. Now, if you feed garbage, you will get garbage. So all these outcome actually depends upon the input data. As much as refined data you can put, you will get much and much better result. Now, what about this bad data? If you put more bad data, output will be automatically more so-called bad result. Now, what the bad data? Bad data can be different type. It can be inconsistent schema. It can be extraneous text. It can be your redundant data, missing value, contextual error, garbage value, null value. All these are so-called bad data. Now, till now, there is no algorithm. If you put the algorithm, all the data pass through that algorithm and feed that into a data, machine learning model, it will clean the data. No. There are for different badness, different algorithm. For redundancy removal, there is an algorithm. For missing data, there are different algorithms. For erroneous text, there are different algorithms. For garbage, say value removal, there are different algorithms. But there is no single generic algorithm which can clean all the badness of the bad data. And that is very interesting. So if you have an algorithm, you put that algorithm before the machine learning model, you feed the data, it will clean the data. Data will be good data. You feed into machine learning model. That works. But how can you know? How come you know what badness is there in that particular data? Because there is no generic algorithm. So that's why all good data are look almost alike. But bad data are bad in their own way. Because badness is different for different bad data. So that's why we need lot and lot of data. But there should be something which is called the data should be good data. If it is not good data, if it is so-called bad data, ultimately the whole predicted model will be a failure model. So we cannot have some heuristic strategy which will tell this much amount of data you require for machine learning. No. Till now, there is no as such algorithm which will tell you that this much of data you need for any machine learning algorithm. You need more and more clean data. You need more and more, I'm coming to that part that is called the variable data. So you need more and more clean data. As much as data you can provide to your machine learning model, so-called good data, so-called clean data, the model will be more and more robust. So we need data. But why we need data? Because for deep learning, the whole technique is called the memorization technique. So if you have a number of points, you are trying to interpolate some other points. So that is the idea. Now, the main limitation of any neural network is they fail to understand the underlying relationship in between the data. So machine learning model, if fail to understand the underlying relationship in between the data, you need to feed many variants of the data. What I'm saying is, you are capturing the image from Taj Mahal, one particular angle. You have 1,000 data. But this all data are similar data. So if the data are 1,000, if are taken from a proper shape, proper angle, one single angle, there is no variability. It failed to understand the underlying relationship. So that's why you need all those images from all 360-degree angle, all 1,000 images. Then only it will be meaningful. So it's not about big data. It's not about clean data. It's all about big, clean, variable data. As much as variability of the data will be there, as much as clean and variable data will be there, your system will be much more robust. You need to train your system with robust system. If you want to come up, you need variable data. But what the problem of deep learning? The deep learning main problem is it failed to identify, as I said, that how can you inherit underlying pattern? It's far away from integrating the abstract knowledge. It simply tells you it works fine. It gives you this result. Say, for example, a 7-month-old infant, a baby, another infant. If you train that baby, your abstract knowledge rules, he can come up with some certain rules that these things I will do, these things I will not do. A small number of unlabeled examples. But think about deep learning. Once you deploying deep learning, it failed to understand the abstraction of the data, the variable definition. Once the verbal definition is missing, you need to train your whole model with millions and billions of data set. So that's why robust deep learning framework always demands more and more clean and so-called variable data. It's not only big data. So enough quality training data is required. But in medical imaging, the major issue is collection of data. Now, say for example, if you're talking about, say, better generalization, if you have a single dot, you are trying to generalize. If you increase the number of dots, you will see generalization will be much, much more better. Linear regression, if the number of point increases, the point estimation will be much, much more better. If you talk about KNN, the number of data point increases, so automatically you will see the predicted class will be much, much more better. If you go for any kind of hierarchical structure, if you increase the number of nodes, you will see the root splitting structure will be better. So you need more and more data point for better generalization, better point estimation, better data, say, visualization point of view also. So that's why data is important. But our problem is in medical science, majority of the cases, we are happy with 500 X-ray. We are happy with 100 CT images because we don't have data. We have crunch of data. Now, how can you deploy machine learning algorithms where the data size is less, where the intrinsic nature of deep learning framework that demands data? But actually, in reality, we have crunch of data, limited data. So small data problem is the biggest challenge. It's not about big data problem. Rather, we are talking about small data problem. Once the data size is 50, another size, the data size is 50,000. Now think, if you train your machine with 50 data and 50,000 data, it's very high chance that the 50 data will give you a result which is near about 100%, which is nothing but overfitting case. But 50,000 will not give you 100% results, which is not a kind of, maybe you can say, correct result you are getting. Second case is outlier cases. 50 cases, 2 outlier. 50,000 cases, 2 outlier. The first case is something very problematic because 50 data, 2 data are outlier. So outlier is a big issue of small size data. And another thing is, once the data size is less, the variability will be revolved. The variance will revolve. But for the large size data, the variability, the variance is, it's very low. It's not very high. For small size data, it's always high. Variance is very high. So these are the typical issue of dealing with small size data problem. Now I'm talking about some interesting, area which is called the ImageNet. ImageNet, many people use for nowadays for transfer learning, for different transformer models. One is called the ImageNet. It's given by Professor Lee, Stanford University in 2009. Professor Lee from their group, they hand annotated, they marked 14 million data, 80,000 distinct category. So cat, rat, hat, mat, 80,000 category, 14 million data. Now, once there is an image vision computation actually started long back in 2010. So once in 2010 it started during the period of shallow machine learning, the recognition error, the error was 28%. So 28% cases from 40 million data set, 80,000 distinct categorization, the machine can fail, which was good enough. But after, in 2012, once AlexNet introduced, there is a paradigm shift from the shallow machine learning to deep learning. The sudden decrease of error rate was 10%, from 26 to 16%. Now you can imagine how efficient those deep learning frameworks are. Gradually, in 2015, once ResNet introduced, the error rate was lesser than the human error rate, and that is 3.6%. So once it is lesser than the human error rate, means human can make error from 14 million data set, 80,000 distinct categorization, but ResNet failed to do that. And that was something fascinating. Now, once we are actually moving every year from this ImageNet competition, every year the error rate is getting lesser and lesser. Now we need to understand how complex the models are. Professor Hilton in 2012, he come up with an interesting work where he reported, forget about 80,000 categorization. Just imagine you need to categorize 1,000, not 80,000. For 1,000 categorization, how complex the model is? The complexity is you need 60 million parameters, which need to be tuned. 60 million parameters which need to be tuned and 6.5 lakhs of intermediate nodes just to categorization 1000. Now think about it. If the size is 80,000, what will be the complexity of the intermediate nodes and intermediate parameters? Now, without understanding this philosophy, if someone can simply hybrid two different deep frameworks, say for example, someone actually deployed, say, RESTnet with some BGP. Now the complexity, the number of parameters, the number of intermediate nodes, what will be the complexity? It will be huge. So that's why in medical imaging, the major constraint, the limitation, once we are dealing with deep learning frameworks, hybridization is sometimes it's a big no, because we need to understand the philosophy, how these deep learning frameworks works, and once we combine, how complex this model will be. So that is the actually challenging task, to identify the number of parameters and the intermediate nodes. Now, in reality, the problem is completely different. The main challenging part is whenever we are talking about some real life objects, the object taking from a proper lighting condition, proper background, proper shape, but actually in reality, the things are different. Different background, different lighting condition, different angles. So once there is a partial occlusion, the object is something, some part is missing. The object color is something somehow faded out. So in vision computation part, from a manually, if you try to do, the missing information can be rebuilt immediately. But we are far away from actually replicating the object, the recognition process, the capability, which is very, very difficult task. Only is a cognitive, you can say the whole pattern needs to be injected. So whenever we are using some CNN, the deep learning framework, just 2 minutes, please.
Yes.
And yes. नीचे अच्छा आपने नहीं जाना, just 2 minutes please. So that's why one of the limitation of CNN, I'm talking about the CNN, think about it. Once we are dealing with CNN, we are training the whole model with huge data set, where more and more generalization and rationalization is important. Why? What is the limitation? What is the main challenge of using such kind of ImageNet or CNN? Now, ImageNet is a particular data set which I talk about 14 million data. These all data sets of ImageNet are so-called good data, because all those ImageNet data, if you look into carefully to ImageNet data, the left-hand side, the chairs looks like something like this. So all are taken in proper lighting condition, proper shape, proper angle, and all are so-called good data. But that system, the overall ImageNet, is never getting trained with the chairs, which is shown in the right-hand side. So these are so-called bad data. So based on the ImageNet, if you are trying to come up with any kind of model design, your system is getting totally biased, because you are actually only trained with the good data. Your system is never getting trained with so-called bad data. So that's why, even though ImageNet is a huge data set, 14 million data, we use for many, many cases, many transfer learning model design, but ultimately it's proven that it's flawed. So the main flaw is all the images are so-called good data. It's never actually trained with so-called bad data. So we need to understand that whenever we are using any pre-trained model, we need to understand that the model should get trained with good data along with this bad data too. Now here the CNN, even it's not the variable size, as I said, if you're not getting trained with all different angles, ultimately your CNN will not work, because you need to train your machine in such a way that the main limitation, as I said, the understanding the underlying relationship in between the data that needs to be actually explored, which is the main limitation of CNN, as well as you can say the neural network, because it's failed to identify the underlying relationship. So you need to capture the images from all different angles, all variability. But what about this CNN? Once we are talking about only CNN, just give me this slide, but look into this slide. There is one intermediate step is called the pooling. So once you talk about the pooling, say for example, 3x3 matrix. Now in this 3x3 matrix, you are trying to identify the max or maybe the mean value. So max pool or mean value, and you are throwing remaining all 8 pixel. Now think in a different way. Amongst those 8 pixel, without understanding the underlying relationship in between the pixels, you are simply discarding. Who can say in some other application, on some other time, it might happen amongst those discarded 8 pixel, 1 pixel can be efficient, effective, and maybe it will give you better result. So pooling is nothing but a disaster for CNN, which is actually said by Professor Hilton. He said that no, pooling is a kind of thing where you are trying to find out the max or the mean. You are throwing remaining all pixels without understanding the underlying relationship in between the pixel. So that's why pooling is nothing but a disaster, even though we use CNN. And if you look into these two images, you will see there are 2 eyes, 1 nose, 1 mouth. If you simply take all these things as a point, say this is your face, this is your eye, this is your nose, this is your mouth, and simply toggle all those places, you will see your CNN will give you these faces are not similar. So 2 images, you are simply changing the position, and once you are getting different result, your CNN might not give you correct result. So these 2 images might be, the output might be of these 2 images will be similar. Because even though you position those particular points into different location, this localization will actually not affect the whole CNN model. So these are few of the very basic fundamental limitations are there in CNN. And again, CNN is not so creative like human brain. So we need more data, as I said, and we need more variable data, because ImageNet 14 million data, it's all good, but it's never getting trained with bad data. So what is the solution? Once there is a crunch of data, once there is a crunch of variable data, once there is a crunch of variable clean data, the only strategy we can adopt, that is called data augmentation. So we need to augment our data. We need to increase the volume of our data so that we can create more and more variable data, more and more clean data. That is the thing which we can do. So we need deep learning framework. We need millions of parameters. We need faster training. We need lot data. So as you will say different models are coming, the data size is increasing, and gradually the complexity of the problem statement is getting increasing. Yes, it is always good to invest more and more time and effort for gathering data. Otherwise, it will be a failure case. But in medical data, getting annotated data is very difficult task. As I shown, doctors are spending 2.3 minutes time in India per patient. They are so busy. They can't give you always benchmark data. So time is a big limitation. And another thing is, for different country, they have different privacy protection law. So they are reluctant, or they are sometimes they are bound not to share their data, private data. So patient privacy policies are there. So that's why when we gather the data for medical data, the most issue we actually face is the limited size data. So one time while you are talking about 14 million data, other time you are talking about 1000 X-ray. So data is important, gathering is very difficult. So whenever you are deploying any deep learning framework, you should think about more and more creating of such kind of augmented data so that the volume can be increased, and as well as the variability can be increased so that the system can give you more rational output, more reliable output, rather, better to say. So this is one particular slide where there are a lot of data and data size is given. You can use for your research purpose. Now coming to the augmented part, one type of augmentation which is called the so-called synthetic data. Now almost 60% worldwide data is nothing but synthetic data. So it's sometimes generating original data is very time consuming, costly process, sometimes impossible also. So we need to carry out more and more synthetic data. So synthetic data generation is the main advantage is there is no legal compliance, there is no ethical issue, there is no copyright. So you can create your own Mona Lisa, you can create your own, say, MR image, city images. So in this way, you can create your own synthetic images. So that is the advantage. So after this Gen AI, there are people are talking about this creation of synthetic data and all. But once few years back, once we started working on GAN, the concept was basically the same thing. We created more and more synthetic data by using GAN. Now, data augmentation technique, there are very primitive old techniques Like say, for example, geometric transformation, you simply rotate the image, flip the image, translate, zoom in, zoom out, shaded, elastic deformation, go for contrast stretching, color augmentation, you crop some part of the image, or maybe you change foreground and background, change the say foreground level, background level by changing the alpha tuner, or maybe changing the variance of a kernel, maybe the Gaussian kernel you are changing and increasing number of images. So from one image changing kernels, you can create say 10 images or 20 images. In this way, we used to still do data augmentation. But again, think in a different way. Once we are creating many images by this kind of tuning, this kind of changing the variance level, ultimately all these images are somehow generating from the basic image, the first image. So it's simply nothing but a knowledge propagation. It's the same type of image which not that noise is getting propagated from one image to another image. The noise is getting percolated. So it's a kind of redundant information propagation. So geometric transformation, by which we used to do geometric transformation based data augmentation, but ultimately all these kind of strategy, fundamentally all the images are somehow biased towards a parent image. So that's why it's a kind of similar type of redundant data you are imposing your whole model just to increase the data volume. Ultimately, whatever the result you are getting, it's a biased result. So kernel filtering strategy, random cropness, zoom in, zoom out, all these strategies are fundamentally flawed because you are simply increasing the perturbation level, the noise level into the whole model. So that's why the solution can be GAN. So GAN, what we are trying to say, change from image to image translation. So there is a conditional based GAN can be there. So summer scenario can change into autumn, or autumn can be into winter. And there is some another robust techniques also, which is called neural trial transfer. So GAN is very costly, computationally very expensive also. So that's why alternate cheaper solution, you change the texture, the background, foreground, etc. of an image, and you create many images. Say for example, this is example of a creating of synthetic image. You can see the true city images and corresponding synthetic images generated by GAN. So it's almost closer, very similar. So I'm not going into the detail of GAN, how it works, means the discriminator and the generator, how creates more and more fake images. But ultimately the target is to increase the size of the data volume. And this one is a neural tile transfer. Let's say, for example, studies transform, which is song, the thematic song. You are changing the background, the texture, the color of the image based on that particular song. So in this way, the background and texture, if you're imposing into the image, you can create many images, which can actually help to increase the data volume. So in this way, you can also increase your data size. So these are few techniques. This is one, say for example, Kanagawa wave. You are imposing that whole wave into an MR image, and the MR will give different more synthetic images. You can increase the volume of the data. And another way is called the transfer learning. So once we talk about transfer learning, that is also another similar kind of problem, where say for example, you have a small size data, you are trying to solve a problem. So once you fail to do that problem solving, what you will do, you will try to solve a bigger problem where the data volume is big. So if the data size is big, say for example, ImageNet, so from there you try to solve the problem. And once you gather the knowledge, you pass that knowledge as a frozen knowledge, as a pretend knowledge, and try to solve the problem where the data size is less. So it's basically solving experiences of a bigger problem and passing that knowledge, transferring that knowledge to solve a problem where the problem size is small, the data size is small. So that is the whole idea of transfer learning. And transfer learning is not very computationally expensive like GAN. So many people use these transfer learning models. But the problem is in transfer learning, if you're doing the transfer learning model design based on some model which is actually biased, say for example, as I said, the ImageNet, all the data are so-called good data. So transfer learning model will be trained the frozen knowledge, which you will actually transfer, that is basically good knowledge. So good frozen knowledge, because it's all good data. So you need to train your system with bad data also. And sometimes transfer learning model, we need fine tuning. So the lower level, there will be no as such change, but in the upper level, the noise needs to be imparted so that the transfer learning model can be redesigned and it can be deployed into particular problem solving. So if all the images are of similar domain, maybe the problem solving will be easy. If the problem statement is different and the whatever the image you are using for the solving the problem, images are different domain, then you might need some fine tuning. So this is called a kind of, you can say, pre-trained model result enhancement by actually changing the fine tuning those last layers of those models. So that can be done. And another thing is that one-shot learning, where there is no as such training data. You have one data, for example, the model can't look into the examples. It can be 0 shot, it can be 1 shot, or it can be K shot. In medical imaging, it's not hugely used, but nowadays few shot learning many people are using, but not 1 shot and 0 shot too much. The idea was actually given by NVIDIA, where they try to find out the face recognition problem, but they actually this particular problem, if you're wearing a mask, if you're wearing a glass, or if you're wearing a hat, the result might be different. So it needs sometime fine tuning. Two pictures containing the same dog or the same cat, it's not actually detected by such kind of thing. It's difficult, but still people tried. In 2015, there is a paper which comes in PLOS Biology, where first time actually it was reported this how one-shot learning unfolds the brain imaging. So this is long back. In last 10 years, many people actually work, but mostly on few shot learning, few on 0 shot learning. Now I am talking about some little bit of challenges. In 10-15 minutes, I will try to conclude. One challenge is called the patch-based training. Instead of training with a whole image, you can make it small patches. And if you train with the patch-based training, the model will be much more robust. So talking about the semantic segmentation, which is basically the pixel-based segmentation. So instead of whole image, if you go for pixel-based training or maybe patch-based training, the training will be much more efficient. But once you do for patch-based training, once you go for this sampling strategy, you need to understand that this patches should not overlap. If they overlap, the result will be good, but ultimately the result actually maybe high accuracy will get, but computationally it is extensive. So there should be a sliding window protocol like kind of thing, which will actually slide and capture those slices, those samples, and give you a better convergence, faster convergence. So overall, what will be the patch length? What will be the patch size, the sample size, that need to be identified correctly. It should be determined based on the size of the image. I mean, if the image size is too big or the image size is too small, based on that, the size of the patch will be different. So if this is how instead of, training the whole model with a large size image, you can break it into small patches, then patch-based training might give you sometimes better result. So one suggestion, this is one of the weekly supervised learning. So if you don't have annotated data, if you don't have, all the data are non-annotated, then what we'll do? We will go for supervised or unsupervised. So we need some in-between solution. So it's not always, say, too expensive, less accurate, or maybe accurate kind of thing. Not transfer learning, say, supervised or semi-supervised learning. In between these two, if you have unstructured data, you can go for weekly supervised learning strategy. Say, for example, a doctor don't have time to benchmark the data. An engineer is doing the benchmark for someone. Now, once the engineer will benchmark, he don't have domain knowledge, but he can give an idea that this is the tumor. So obviously, there can be some error. So considering that delta error, if you come up with a benchmark data, that is called a weekly supervised learning framework. So weekly supervised is a kind of cheap annotation technique. Weekly supervised learning kind of heuristic strategy can be also adopted, by which, considering some certain bias and error into this model, you come up with a, say, level data that is called the weekly supervised framework. This is sometimes very effective, because if you don't have benchmark data, if you don't have ground truth, it's better not always go with no annotation. In between something, considering some error, non-expert can come up with a cheaper solution. And that is basically the idea of weekly supervised learning. Sparse annotation, instead of training the whole model, Few of the pixel works, few of the pixel not works. Say for example, ROI pixel works and ROI non-ROI pixel, it's not works. So ROI pixel, you try to, there is a switch on off kind of thing. So just like sparse matrix, the number of zero element will be much more higher than the non-zero element. Here also in image, the number of zero element might be higher, non-region of interest area. Lesser will be a region of interest, which is on 1. So in this way, which will trigger, which will not trigger, that you will decide, so that the whole model will getting trained with only the positive pixels rather than the zero pixels. Or you need sometime negative data set also. It's not about always the positive data. If you train with your model with only positive data, the discriminant power of the classifier will be very less. So to enhance the discrimination power, you need equal, the positive, the negative data set. So it's not about always positive data. False data we also require just to discriminate, powerful discrimination of the classifier. That's why effective negative set is important for classification technique. Another thing is class imbalance problem. It's not talking about only the data class imbalance problem. I'm not talking about the smooth kind of thing which you deploy for balancing your data. Rather, in medical image, some part of the image is very, actually effective, like say, for example, region of interest. Some part you don't require. So which part you will actually work with, which part you will not include for the training or the model design, that need to understand. Where the patch-based training actually helpful, that this much of patch I require, this patch I don't require. I need ROI patch, I don't need non-ROI patch. So sparse matrix or the sparse annotation or this class imbalance problem and this patch-based training are almost similar, which actually tells you that this much of data you can include and this data you should not include to make more faster result, more accurate result. So that is a way. So these are the few of the things. Another thing is that overfitting cases. We see many of the cases, the validation matrix, if you look into it, you will see the training accuracy is getting improved and improved. But validation matrix, if you look into this matrix, you will see the value is getting lesser and lesser. So that time you can say it's in getting overfitting cases. So not only improving the accuracy, we have to look into the validation matrix also. Now, sometime we need, once there is a high, you can say getting training data is getting training result is very high. Validation is not that much high. So that time what you need to dememorize the training capability of the whole machine. So how to dememorize, lower the capacity of the memorization technique. For that, you need to go for different techniques. Say, for example, you can go for L1, L2 regularization. You can go for dropout, etc. So that you can reduce the whole memorization power of any model. And another thing is the learning rate. Basically, even many of the cases you will see there is an optimization technique we use, which is called the stochastic gradient algorithm, which is estimating the error gradient for the current state and the input state, the training data, current state and the training data. What is the error rate? So for that, we use this optimization technique. And for this particular technique, we need learning rate. Weight need to be balanced. So once we need to tune the weight, upgrade the weight, there is a factor which is called the learning rate. And learning rate is basically the step size. So what will be the prominent step size for your particular model? So that's why it's a kind of optimization technique again. So that's why there is no hard and fast rule for this model. This will be the value of this step function or the learning rate will be this. But there are different optimizer which actually helps you to come up with a rational decision-making process for using of optimizer. There are mostly we use the ADA delta or the ADAM. These are the few of the optimizer which helpful to optimize this rate, which is which plays a significant role amongst all those parameters. As I mentioned, there are too many numbers of parameters. Few of the parameters are very efficient, effective. One is the learning rate, which can change the whole model. And last one is the gradient vanishing and exploding. Vanishing, I think all we know that, if it is approaching towards a zero, the error, once you check the gradient, you will see there is a very small gradient, the input and output. We used to say this is a vanishing gradient problem. But reverse is also true, which is called the exploding technique. So if the input and output is getting, say, not closer, rather it is getting larger and larger and larger, there is never be able to converge in one time. So it's a kind of diverging problem. So once the gradient is getting diverges, it's called the exploding gradient problem. So once we go for any kind of machine learning model design, if we face such kind of vanishing problem, we also need to understand that there is another problem which is called the exploding problem. The solution can be, there are different solutions for this exploding and vanishing problem, which is called the descaling, but rather better to say deconvolution. So deconvolution is a strategy where the batch normalization, gradient crimping, these are the techniques which actually deployed for this kind of gradient vanishing and exploding process. One pixel can make full. So if you remove one particular pixel, the result for cat from dog can be sheep. So one pixel can make the difference. It's an interesting paper which comes in TEC in 2019, which shows that one pixel whole result will be different. So deep learning are quite good in large fraction of cases in given domain, but it can be easily fooled. This is a one pixel attack. You can go through this particular problem statement and the paper. One pixel attack is very interesting paper where the authors reported that one pixel can change and one pixel can fool the entire deep learning framework. Now coming to the explainable AI, it's all about the believing something, the result which you are achieving. See, if you are getting 99% accuracy, you have to convince the people. So once we are talking about the explainable AI, we talk about the explainability and the performance, the linear model. If you move from linear model to say Bayesian, from Bayesian to statistical model, from statistical model to say go for random forest or maybe any deep learning framework, you will see the explainability of the model is getting quite lesser, but the performance is getting improved. So we need to come up with a trade-off in between these two so that people can trust. So why should I trust you? That need to be answered. Even if you're getting very, very good result, ultimately you have to justify your result. So that's why explainable AI is good. But there is another way of thinking, that is, why should I trust the way explainable AI is asking me to trust the model? So the way you are trying to making someone to convince, that way is correct way or not, that need to be also understand. So those who are working in XAI, they should also explore counterfactuals, which is called what if scenario. What if scenario means if this scenario occurs, synthetic scenario, then what will happen? So it's not about explainability, even if you are trying to go for the counterfactuals, where you are trying to find out what if scenario, if this scenario occurs, what actually happens. So counterfactuals also need to be studied. But here it's a simple example of lime. In this Labrador, which particular portion of the image is trying to explain by this explainable AI model, we are trying to find out from this intercept V3 that which part is telling that this is a Labrador. So this needs to be justified, this can be explained. But if you look into this explainable AI, the data quality, the causality, the correlation can be same, but ultimately it doesn't make any sense sometimes. Inherent bias can be there, but the last point is very, very important. Explainable AI always talks about AI model, but it never talks about the data which is used. But in medical imaging, mostly we are data focused. Whatever the data you are using, even many of the machine learning model design. But XAI always talks about AI models. It never talks about AI data, which you are feeding for the whole model. So that is one of the major limitation of XAI. Lastly, whenever you are we are talking about this deep learning frameworks, we need to understand that whenever we are fusing, whenever we are hybridizing, using such type of huge number of parameters and intermediate nodes, we are generating carbon, emitting carbon. So what will be the carbon footprint of these models? So whenever you are talking about any kind of complexity of a model, it's not about the pace complexity or not about the time complexity. Now majority of the places, the journals where people are asking, the reviewers are asking, what is the carbon footprint of your model? So those who are dealing with SDGs, one of the goal is zero carbon. So if you are dealing with deep learning framework, you should always think about it, how much carbon is getting emitted. And the last slide. One thing is we are not substituting doctors. We are actually helping the doctors by providing this CAD system, medical imaging and all these things. So machine learning is always good. So that more data or less data, which actually tell by, maybe the future it will be decided. But the thing is, nowadays, machine learning can be intervened by human, which needs to be fine-tuned more. So that's why human in a loop machine learning is now very, many people are working in this area. And synthetic data, we are creating more and more synthetic data, but we need to stop somewhere. We need to think that how much synthetic data is good enough. So is fake data is real enough or not? So how real enough, that need to be understand. And lastly, so it's a very simple line, but very strong line. The painter actually creates, but LLM recreates. So whenever you are dealing with some synthetic data, remember one thing, the painter needs to be created. So somebody should create, then only can be recreated. And lastly, machine unlearning. This is one of the interesting terminology in medical area, mostly in medical area, you can say. Say, for example, today you shared your personal data, one chronic disease data. Now the machine is getting trained. So from one particular place, there are a lot of people, they are giving data, machine is getting trained. And after 10 years, once the machine is getting trained, you understand that no, I should not share my data. And you started revoking your data. You are reclaiming your data. Now what will happen? The machine will retrain, which will take a lot of money, lot of effort, lot of time also. So it will not retrain. So we'll simply discard, say, from, say, 1 crore data, 10 data, but that will not affect the whole model. We will remove 100 data, that will not actually affect the whole model. That is called machine unlearning. So forgetting the data. So if you're trying to forget, because many of the countries, they are, because of legal issue, their data policy, they are reclaiming the data. So once you start reclaiming the data, the model needs to need not to be retrained. It should give you the same outcome, but the data you can actually remove from the whole model. So the idea, the algorithms, there are 2-3 strong algorithms are there, which is called machine unlearning strategy, which is very crucial for medical imaging, especially healthcare imaging, because they are deals with lot of, very sensitive data. Thank you very much. It's always hard to give online talk, but I tried. So if anybody having any query, I have some issue with my machine. So you can type, I can try to give my reply.
Nilanjan sir.
Yes,
Very
sir.
good evening.
Good evening.
Good evening, sir. Yeah, thank you very much, sir, for accepting our invitation and
Thank you,
finding
sir. Thank you.
time from your busy schedule. I think 2 days
Thank
back
you.
you landed in India from Italy. Yes?
Yeah, sir. Actually, your voice is not clearly audible to me. So that's why the problem.
Okay.
No
Okay,
problem,
okay,
sir.
okay. Fine, fine. Thank you very much. Thank you very much.
Thank you. Thank you, sir. Thank you.
Yes, yes.
So anybody having any query, to please write. I will try to answer.
Hello. If anybody has any queries, sir, I have one query. Hello, sir. I'm audible.
Yeah. Sir, how to minimize outliers? That is one question. So, see, the problem is you can't remove outliers. Say, for example, you are dealing with k-means. Now, in the k-means, all the data is this place, one is your outlier. Now, if there is one outlier, there can be one class this one, there can be one class this one. If you simply discard the outlier, the result will be completely different. So that means sometimes the outlier is very sensitive. But we need to understand that sometimes the outlier is not noise. The outlier can be data itself. So without knowing that it's a noise or it's a data, if you simply discard, then outlier is something which actually plays a significant role. You can't discard. So data is data. Even it's an outlier, you can't simply discard. So that's why it's not a good strategy to always thinking for discarding the outliers. Is it possible to remove pooling operation? No, because pooling is a fundamental step of convolution neural network. So the who actually invented this whole thing idea, he told in a big conference, AAI conference, that pooling is a disaster. And ultimately, if you think in this way, you will see it's a kind of, simply we are discarding without thinking anything. But see, say for example, a good student in first year, 3 are bad student. So you can't discard all 3. It might happen in the final year amongst those three can be one of them can be a good student, can be first. But in max pooling, there is no option. So that is you can say it's a kind of thing which we have to take forward. So CNN, we can't exclude this step, this pooling step. How to identify the filters in deep learning? Identify means the filters in deep learning means for which purpose? Can you write?
Hello, sir. I'm audible.
Yeah, audible, sir.
Sir, like the filters size we can define, number of filters we can define. Number of filters we can define size.
I got your point. Sir, sometime number of output divided by 2. Some people used to do number of input divided by 2 plus number of output divided by 2. But there is no rational way. It's again something, it's a kind of trial and error. There are a lot of places, means these numbers are decided based on the application. So there is no hard and fast rule, means by which you can decide that this number of intermediate filter will be good enough. So, I don't think so, sir.
How CNN or any architecture of CNN decides the actual the numbers in the mask while convolving with the image. For example, if you have 3x3 size filter, so whether it's a loopy filter, vertical line, diagonal line, how these filters are defined?
What happened? Every filter you are using, you are trying to extract more and more minute features. So in which level of minute level you are going, based on that, you have to decide that, okay, this number of minute level feature I will try to include. So based on that, the strategy will be something like that. Okay, up to this, I need the minute feature so that I will get this result. So that's why I'm saying there is, say, 6 layer or 9 layer or 10 layer. What will be the number of intermediate layer? That needs to be decided during your model training. Okay, I am good enough with this result. So it's not about means fixed number. This is a 6-layer convolution neural network I will use. Based on the application, how minute level features you are going for, based on that you are trying to find out what will be the number. But there is, I don't think that there is no rule for this, that this is the number intermediate layer should be. But neural network, intermediate layer neural network, there are some conventional way. As I said, number of input, number of output divided by 2. There are some strategy, but that don't work. Always don't work.
But how CNN decides it? How CNN decide?
CNN never decides. Sir, CNN, sir, the way you design the model, it will work. CNN will not explicitly design for you. Means it will not decide. You will decide. But how you will decide, there is no heuristic. There is no simply adaptive technique by which you will, okay, it will automatically adopt this number of layers. No. But you have to, it's a kind of trial and error. You have to give, okay, up to this, I am happy. So CNN can't create its own number of intermediate layers, this number of layers. No.
Yes, true.
Thank you. I think I need to conclude now.
Yes, sir.
So anybody having any query? I don't know why my speaker is not working today, because the speaker is not good. That's why maybe.
Sir,
there is no. Okay.
Yeah.
Any question?
Yeah. Any question, participants? Thank you, sir.
Thank you, madam.
Yes. So thanks a lot for such an informative session. So just session. I would like to request Mrs. Bharti Sahu, ma'am, to deliver the vote of thanks. Are you there, ma'am? Bharti, ma'am?
Yes, I'm there.
Yeah,
before that, I want to say something. We know sir is very busy, and congratulations, sir, for your high number of citations for your papers. I know it's despite of your busy schedule, and I think you were there in Italy, and I think day before yesterday you came to India. You landed here in India, and you accepted our invitation on the short period of time. So definitely we want to see you on our campus in the offline mode to interact with the faculty members and students.
Thank you, sir.
So we are really thankful to you, sir.
Yeah, one more point I want to add. Even though the sir were outside of India, he was just giving.
Every alternate month I am going Pune, madam. Last month, last month I was in Dubai Patil, another campus. So
No,
It's
sir,
very
but
Yes.
it was very great that you are outside, still you are responding to messages, WhatsApp chats. Really,
travel a lot of traveling.
thank you.
Okay.
Yes, yes, Bhati ma'am, please deliver the vote of thanks.
Yeah.
Yeah, I
Good
request
afternoon.
participants to switch on the camera so that we can take the screenshots.
So, good afternoon, everyone. So, on the behalf of the Computer Department of Engineering, the Dr. D.Y. Patil Institute of Technology, Pimpri, Pune, is my proud privilege to propose the vote of thanks for this today's enlightening sessions. First and foremost, I extend my heartfelt gratitude to our distinguished speaker, Dr. Nilanjan Desai, for taking the time to join us and share your invaluable insights on the challenges and the state of art solutions for the deep learning, medical images as a case studies. Your deep expertise on engaging the presentations on the CAD, how to impose the patterns, segmentations, what is the growth truth, augmentations, and the different challenges you have explained in the presentations, and have truly inspired and enriched our the faculties and participants alike. The way you connected the theory with the real examples, applications, which was very informative for us, which has the participants has also connected with that particular things, those who are doing the research work, so they will be getting very help from these presentations. So we are truly fortunate to have you with us today, and thank you for adding immense value of your academic ecosystems. I also take this opportunity to thank our management, Honorable Secretary Dr. Somnath Patil sir, our respected Dr. Dheeraj Agarwal sir, Director Central Corporate Relations, Dr. Nitin Serje sir, Principal, and our Head of Department, Dr. Vinod Kembone sir, for this continuous supports and encouragements in organizing such an impactful events. A special thanks to our faculty members and organizing committee who experts behind the scene made today's session a smooth success. Lastly, I extend our sincere appreciations to our enthusiastic participants for their active participants and eagerness to learn. Your curiosities is what keeps such events meaningful for us. So let us take this inspirations from the today's talk and apply it in our the academic and the professional pursuits with the renewal zeals. Once again, I thanks to all of you and our guest, Dr. Niranjan Dey, sir, for being with us. Have a great day, sir. Thank you, sir. Over to you, ma'am.
Yes, yes, thank you, sir. Yes,
Hello.
yes, sir.
Ma'am,
Yeah,
share the
Yeah,
link
ma'am.
and like can declare session is over. Share the link so exactly in
Yeah, sir.
attendance.
Ma'am?
Already link has been shared, sir.
shared in the
Yes,
chat
yes,
box. Yes, sir. Yes,
yes, yes. Okay, okay.
yes. Okay, sir.
Thank
Thank
you,
you.
Thank
sir.
you,
Thank you, sir,
Nilanjan sir. Thank
for
you.
taking us.
Thank you, sir.
Yes, participants may leave the meeting.